Okay, good morning everyone. I'm Dominic Farris. I work in the Human Power Lab now with Greg Sawicki, and I'm particularly interested in making measurements on humans. And I've never asked the IRB, but I'm pretty sure if I went to them and said I wanted to put sonomicrometry crystals in a human muscle and have someone run around, they wouldn't let me do it. I know one example, an isolated example of a tendon buckle being used in a human, but I don't think that's something we're going to do on a regular basis. So in the last sort of 15 years or so, people have started to apply ultrasound imaging, particularly BMode Ultrasound imaging, to look at human muscle mechanics in vivo. And so here's an example of the ultrasound probe that I've primarily worked with. We particularly like this one because it doesn't have a big handle sticking out the back of it like you might see with most ultrasound probes. And for reasons I'll hopefully get to later, that's a good thing. It's got a nice low profile. But how does it work? Well, I'm not a physicist. Yes?
How much does that cost?
The probe itself, I think, is around a couple of $1,000. Is that right, Greg? The whole system that we use is about...
I think it's about $10,000 for the whole system.
Yeah.
It's relatively cheap compared to buying from a big company like GE or Aloka is one company to look at. Telemed. This is a Telemed probe. Relatively cheap, pared down, but gets you only what you want. No extra bells and whistles. Just a pin.
So, I'm not a physicist, but it works by a reverse piezoelectric effect in this case. So if we stimulate, we have a series of piezoelectric crystals in elements along the probe, and as we stimulate, one of those elements vibrates, creates a sound wave, which is transmitted into whatever medium is underneath the surface of the probe, and essentially, when it meets another medium, when that sound wave hits another medium of a different density, some is reflected, some is allowed to continue on through. The reflected signal goes back to the transducer and is recorded by the piezoelectric crystal, and the strength of that returning signal, in the case of BMode imaging, is converted to a grayscale value within our image, with strong signals showing up as bright white. So this continues along the probe, and in this case, you would end up with something that looks a bit like this, where we change density, we get a bright white line in our image. Sorry? So BMode refers to the fact that you are getting grayscale values to generate an image. In A mode, you would just get a value for the power of the signal coming back. And so we can take advantage of this when looking at muscles because elastic tissues have different densities to the other tissues in the muscle. And so what you get is the elastic tissues showing up as bright white lines, other tissues showing up darker. And if we look at, this is the same image I used from my talk the other day, for those who saw it. If we put an ultrasound probe on, in this case, gastrocnemius and soleus muscles, we get an image that looks like this, and the skin is at the top here. This is deeper into the leg, this is towards the knee, and this is towards the ankle. And what you can see in here, this is the distal end of medial gastrocnemius, and here is soleus, and we can sort of outline them there.
This is equivalent to a slice.
Yes, sorry.
How thin is the slice, or how much control do you have over that?
In terms of the width of the slice, the thickness of the slice, you don't have any control over that other than the hardware that you particularly buy. I couldn't tell you offhand the thickness of the slice, but essentially...
You taper it down from whatever the width of your elements are on the left side, basically understanding how it works. So it'll be kind of a triangular wedge starting from the thickness of the penis and like the actual crystals and the tapering down.
And you certainly have tapering in the plane of the image as well.
And
Slightly
how
curved.
fast what's the exposure time and how often can you take a picture?
So the exposure time depends on the resolution that you want. If you want high resolution, you have to take a lot of scan lines. If you want a lot of scan lines, it takes a little bit longer. So we, with our system, typically don't get above 50 hertz in terms of sampling of images. That's because if we want faster sampling than that, we lose image quality and lose resolution because you need fewer scan lines in your image. There are systems.
The max scan rate would be 125?
The maximum with our system that we can get up to is about 90 hertz. There are other systems. One of the things you will get with more expensive systems is you can get up over 100 hertz. I haven't actually seen firsthand the quality of the images you get, and I don't know if they are making a trade-off with image quality to get that sampling rate. But so yeah, so we can see those two muscles in this image, and hopefully you can see, particularly in medial gastro up here, you can see a light and dark banded pattern running through the muscle, and soleus, you can see the same thing, running in the opposite direction, so the pronation angle is in the opposite direction here. And so we can directly measure from our images the length of the fascicle and the pronation angle of the fascicle as well. You would eventually get to bone. This image the depth is 65 millimeters. So yeah, you would eventually get to bone, and what I tend to do is turn down the gain once you get past the muscle of interest, because I don't care about that signal. So it appears dark here, you could get deeper images. Depending where you are on the muscle, depends what you'll see deeper than this. You might see some of the, something like flexor hallucis longus underneath. Might be a muscle that you can see. But yeah, that will totally depend on where you are on the leg. And you can go deeper than 65 millimeters if you want. That will also affect your resolution of your image though. So those are some things we can directly measure. Something else we might be interested in looking at is the displacement of the myotendinous junction. So if I stay with this image for now, this here is the myotendinous junction of gastric memius, where this sort of comes to a pointed V. We can also see that on soleus. So I've got another image here taken further down the leg, so we're more down here somewhere now. And it's in the same plane, but rotated 90 degrees. So this is the skin, deeper into the leg, ankle down this way, knee out of the image that way. And here you can see the distal end of soleus. And so we can also see the muscle tendon junction of soleus, just to point that out there. And I've tried to highlight in green here the Achilles tendon. So we can also identify tendinous structures. There's the myotendinous junction. And we can look at other things we could measure directly if we were interested, muscle thickness or muscle width, depending on the orientation of the probe. If we flip the probe around the other way, so now we're taking a transverse plane through the leg, so a section, if I chopped through your leg that way, we can look at things like the cross-sectional area of muscles. So here I haven't got the whole cross-section of the medial gastric memius or lateral gastroc, but with a bigger probe or with a different positioning, you can get one or the other or both in. So if you're interested in cross-sectional areas, we can get those. And if you use motion capture as well to track the position of your probe, you can actually pull together a bunch of cross-sectional areas to get volumes for muscles. So just to demonstrate that we do capture this dynamically. So again, these are both at 50 hertz. Here is someone hopping. I showed this the other day. The video on the right is just someone, this is medial gastric memius now, so we're a little further up the leg. And it's orientated the other way around just to really confuse you, but still skin and deeper into the leg, and here's the muscle. And that video is just someone passively moving their ankle back and forth.
Do you have to overlay the images one at a time to get the video not being one of them going in and out of view?
Sorry, I don't quite.
I would imagine that there's net motion going on, distortion, and then a lot of your video would be muscle going in and out of view as opposed to muscle distorted. You have to go and realign your images to get such nice videos like this?
So you can sometimes lose the fascicle that you're tracking. Is that what you're saying? You can lose it out of the view of the image?
It doesn't look good because the cyclic motion is so much bigger than the distortion. You don't have that problem.
I'm not really sure exactly what.
These movies look really nice in terms of that you see distortion. And I would imagine that that sometimes in the video you would just see things going back and forth. And it would be hard to see the distortion because there's just net motion underneath the sensor.
Yes, I haven't had a problem with that. No.
Okay.
It's the short answer.
The way that the muscles are pinning, you know, the tendons coming all the way down, it stays relatively close to the leg, and then you have the other tendon moving up and down. So I suspect that's why this having that issue.
But one thing we do in some cases, which I will show in a minute, is we track the position of the ultrasound probe to get an idea of the relative movement between the leg and the probe itself, or the muscle and the probe. Making measurements at the moment for me is a fairly laborious process. I do manual tracking, just go through in each subsequent image, marking where the fascicle is, or tracking the position of the myotendinous junction in each image. In the last year, Neil Cronin and Glenn Litchwa and colleagues have actually published a paper that shows a nice MATLAB GUI, which they have on MATLAB Central now, for anyone who's interested, which will do some automatic tracking of fascicles in the medial gastric memes. I haven't really had a good chance to evaluate how well I think that's working just yet. So I've got to stick with spending a lot of time sat in front, clicking on a computer screen. So those are the things we can directly measure and directly track, and then there's some other things that we want to know which we generally have to estimate to a certain extent. One of which is the series elastic length. So let's say we've measured fascicle length, we want the series elastic length. A common approach is to take some regression equations from publications like these, and use kinematics to calculate the length of the whole muscle tendon unit, so the whole soleus length here. And taking that information and pronation angle and length of the fascicle, we basically assume that all other length change within the muscle tendon unit, other than that of the fascicle, is due to series elastic length change. So anything in series change length. So a little schematic here, if we have the whole muscle tendon unit length, and we have the length of our fascicle and its pronation, if we measure the length change of the fascicle, correct for pronation angle or adjust for pronation angle, and then assign any remaining length changes to the series elastic element.
So the pronation angle is changing as a function of itself?
Yes, so we're taking this at every data point in time, we calculate down.
Is there any more direct method to get the moment arms and things like that?
To get the moment arms of the tendon.
Right.
Direct methods, there is a method using ultrasound to try and estimate moment arms called the tendon travel method, which was first developed in cadavers, whereby you relate the elongation of the tendon during a passive movement of the ankle joint to the rotation to get the moment arm. I would personally question whether you are maintaining the same tension in the tendon the whole time you're doing that, even if you're claiming it's passive, which is extremely important for that to be reliable. We estimate moment arms from kinematics, typically, and the length change of the whole muscle tendon.
You can't just take the ultrasound and wipe around their leg?
You could, not really, because you can't see the joint center in an ultrasound image. People have done it with MRI. You then have the problem that your moment arm is changing constantly as you move through ranges of motion. So in an MRI scanner, you can hold someone in a position, scan it, move them, scan it, move them, scan it. And then it's going to change for different people. As far as I'm aware, no one's very successfully related moment arm length to something else we can scale it to. So at the moment, I think you've got to, if you want it that accurately, you've got to do it for every single person that comes into your lab, which is expensive, I think, if you want to use MRI. And you need an MRI scan.
But it just seems like, so this is an ultrasound that's directing, it's measuring something very directly, and then having to rely on sort of published information for somebody else from years ago. It seems like that's a bit of a weakness.
It is, actually, and one of the things that I will say and comment on in a minute is I'm going to talk about length changes today that we're measuring. And then another key aspect is most of the time you want to know force as well, and I think Tom was discussing it just now. I think that's a little bit of a weakness at the moment, is trying to get really good force estimates. And obviously moment arms are an important aspect of that as well.
Right here, this chart, is that actual?
Sorry, it is.
The very sharp angle here, right there. Is that normal? Is that just
Oh, that's an ultrasound probe right there.
okay. Is that
So this is what I was going to show you. This is how we attach the probe to the person dynamically. This is Coban wrapped around the leg, over the top of the probe to hold it in position.
So the band is really stiff.
Yeah, so you can just about make out here at the top here. That's the this Coban thing. Exactly, yeah. So this is an alternative for getting series elastic element length. We can dynamically, during movement, using the ultrasound probe, track the position of the muscle tendon junction, as I showed before. And at the same time, we are recording the position in the global coordinate system of our probe using these three markers on the probe. We can get a coordinate system for our probe, and we have a marker on the insertion of the Achilles tendon. So we can find the distance between where our muscle tendon junction is and where our calcaneus is, and we can take that length as the length of the series elastic element as well. That obviously then is not including intramuscular aponeurosis as well. So that's some of the things we can measure or calculate and estimate. Why might we use this? Where might we use this? A lot of it started using isokinetic dynamometry, which is, I guess, our attempt in humans at recreating benchtop odometry that Tom talked about earlier. So we can put someone, here we have someone lying prone in an isokinetic dynamometer, and essentially what this dynamometer does is it measures, you can finely control torque about the dynamometer, and it's important that it's about the dynamometer, not about the ankle joint. That's one of my issues with this technique. And you can also control the angle of this. In this case, it's a foot plate because we're looking at the ankle joint. So we can fix the person in position and ask them to contract, and we can ask questions about muscle architecture, how does pronation angle change, what's the fixed end compliance. So if we keep both ends of the muscle still and contract, how much length change do we see? And we can also, with our force estimates, try and get a handle on things like stiffness and hysteresis of the series elastic structures. So here are just a couple of graphs from my PhD thesis showing force and length change. I think I should probably steer away from saying anything about stiffness based on this week. Within the Achilles tendon, and then some loops that illustrate that there is a certain amount of loss of energy potentially in the Achilles tendon as well. And we've just talked about moment arms a bit. If you are interested more in that, Maganaris is a name that you will want to search for. that was just the publication actually I was referencing. That's European Journal of Applied Physiology. So those are some things we can measure in that situation. Probably a lot of people here are more interested in what happens during locomotion. So here again, we've got some nice blue Coban wraps, so you can see more easily that we've overwrapped the ultrasound probe on the medial gastric meatus. And you can see we can walk people on a treadmill. This person is going to start to run in a second as well. And that can allow us to look at what's going on during locomotion. So I'm just going to put up some landmark studies, or what I think are landmark studies so far. So most people will reference this paper by Ishikawa when we're talking about series elastic compliance in the plantar flexors during walking and running. And the main thing that they pointed out here was that you get some really nice isometric behavior of muscle fascicles during the stance phase, and a lot of the lengthening is taken up by tendinous tissues, which then allows for a catapult-like action of the series elastic tissues, much like Tom described in frogs the other day. Ben Lichwa also used these techniques to look at the differences between walking and running. And the main difference being that you do see shortening of the muscle fascicles the whole time during the stance phase of running, but it is much slower because of the tendon. You would have to shorten your actual contractile elements much faster if you didn't have a series tendon. This is some data that Greg and I published recently. We were interested in how, with changing speed and changing gait, muscle fascicles change their behavior. Here we see that as you walk faster, typically peak velocities get faster and faster. This is bad for force production. It's harder to produce muscular force at high shortening velocities. When we switch to running, we get a much more isometric contraction. We sort of postulated that this might be some reason why we switched from walking to running when we did. Yeah, sorry. So that's pretty much, this was a slide where I was pretty much going to put it out to you. How can we use this type of thing to help with robotics? And there are some things you need to consider methodologically. Probe positioning, there are some guidelines for how best to do that. It's pretty repeatable during and accurate when compared to static movement, static contractions. We still need to confirm some of the accuracy with in dynamic movements. I'm thinking maybe sonomicrometry combined with ultrasound might be good. And I guess I need to stop talking now. So just make sure we have time. Yeah.
So there's something that is coming out, ultrasound elastography, which claims to directly measure tissue stiffness using ultrasound rather than trying to measure features. Have you explored that at all, or do you think it works or can be used?
I am trying to learn about it from reading papers now. I've only sort of recently become aware of that, so I can't really at this stage tell you whether it works or not. But it definitely has potential and would be if it does work, it's going to be a really nice way of looking at the elastic properties of tendons rather than having to make some assumptions in our force estimates in these experiments.
When the medial head of the gastric is contracting during the swing or walk, when does it contract in that swing phase and when launches?
That's a good point. So for anyone who didn't hear, we're asking what's the medial gastroc doing during swing phase during walking and running. The answer is I haven't really focused on that very much. It's not hugely active as far as I'm aware during the swing phase.